Hi everybody. As you remember in our previous lecture, we talked about the fundamentals of Bode plot and we covered how we can draw the Bode plots of first order systems, this is second, for and using asymptotic approximations. Today's lecture will be based on second order transfer functions, but we will start with reviewing the first order case. Okay, let's assume that we have a first order low pass filter which has a pole at -10 location. Okay, so what we need to do? We need to first detect the time constant and cutoff frequency for this low pass filter. Okay, let's start with this. We know that omega c is equal to the magnitude of the pole is equal to 10 radian per second, and time constant is simply equal to 1 over 10 second. Okay, so we know that we can write this transfer function in this form also. If you are more familiar with the other form, 1 over s divided by 10 plus 1, which may be more helpful for some people. Okay, so first of all, what is the DC gain of the system? G of 0 is equal to 1, and from this we know that at low frequencies, magnitude will be dB equal to 0. Okay, so we know that for low frequencies, magnitude will be equal to 0. As you can see, it's already 0. And the low frequency approximation will be valid until we reach the cutoff frequency, which is 1 radian per second. Okay, so after this point, we make a different approximation. As you remember, it's a line also similar to the low frequencies. This is high. But now it is a line which has a tendency, and its trend is equal to minus 20 dB per decade. Okay, so and if you remember, for all first order systems at high frequencies, you need to see a line, approximate line, which has a minus 20 dB per decade tendency. Okay, so this is everything that you need to know about the magnitude of a first order expression. Okay, for the phase, we have three connected lines to approximate the whole phase behavior. And in order to capture the behavior, we need to define two other frequencies, here and here. Okay, so this is cutoff frequency. We label the frequency which is 1 decade after the cutoff frequency in logarithmic scale, and 1 decade before the cutoff frequency, which is 0.1 times omega c. Okay, now we divide the region into three parts: low, medium, and high. In low frequency region, we have constant 0-degree phase. And as you can see, this region is important because 0-degree phase and 0 dB gain means that the system acts like an all-pass filter, with just passing everything until omega is approximately equal to 1 radian per second. At high frequencies, it also shows a constant phase response, and here the phase is equal to minus 90 degrees, which means that the system has a phase lag of 90 degrees lag. Okay, good. And in order to capture the median frequencies, we simply connect these 2 points and draw a line passing through the minus 45 degree and 10 radian per second point. Okay, so as you know, the actual Bode plot exactly crosses this point. Okay, so it's very important for our characteristic, which means that at the cutoff frequency, low pass filter systems shows a 45-degree phase lag at the output. Okay, so this is for this transfer function. Now let's try to speculate what happens if I change the frequency. Changing the frequency changes the magnitude and phase plots in the horizontal axis, okay? But nothing changes. The shape is exactly the same, but we only shift towards left or left based on the frequency. If I add a gain, for example, instead of 10, if I add 100, what I do is I change the magnitude only in the vertical direction based on the additional gain that I added to the system. Okay, so from this perspective, you can easily understand that first order systems share the same picture quality or picture graphical features, but based on the gain and the phase, you just shift the Bode plots from right or sometimes in vertical direction. Okay, now let's talk about second order systems. Okay, this is a second order system and it's a specific second order system. We know that it has a repeated root, so zeta is equal to 1. Okay, which means that it's a critically damped system. So for critical damp systems, we have a repeated root, and the good thing is drawing Bode plot for critical damp systems is easier than overdamped and underdamped case. So what we do is very simple. Instead of writing this like this, we write this as a square of a first order system, right? It's true. Okay. And we already draw the Bode plot of 10 over s plus 10, which is shown here in the magnitude and here in the phase. Okay. And we will try to understand the Bode plot of G based on this subsystem. Okay. So let's assume that this is equal to P of S square, where P of S is equal to 10 over s plus 10. Okay. So let's look at the magnitude. M of G is equal to 20 log 10 magnitude of G of J omega. Okay, this is equal to 20, so let's just get log 10 P J omega square, which is good since it's square and this is logarithm. We simply do this 2 times 20 log 10 magnitude of P J omega, which is great, which is simply says that M of G is equal to 2 times M of P. It's very simple. For each frequency, I look at the magnitude response of 10 over s plus 10. I multiply it with 2 to obtain the magnitude response of G. Okay, let's do it. And let's change the color like this. Okay. So 0 times 2 is equal to 0. Let me just color this. Okay. Here, let's concentrate on this point. Okay, minus 20 times 2 is minus 40. If I look at this, minus 40 times 2 is minus 80. If I do it for all of the points, I can clearly see that it is also a line, which is an unexpected result. And different from the first order case, it has a tendency of minus 40 dB per decade. Okay, good. So we covered the magnitude response. Let's look at the phase. Okay, so if you look at the phase response, we already know that. So let's clean everything to be just okay. So this is true. Let me clean everything, and I will try to explain the phase. Okay, so phase of G is equal to phase of 2 times P times J omega for each omega. Okay, so it's 2 times the phase, and we know that 2 simply goes here. It is 2 times phase of P J omega. It's great. It says that phase of G for each omega is equal to 2 times phase of P omega. So I will do the same thing with the magnitude. I look at the phase at each frequency, such as the one here and here. I multiply with 2 to obtain the phase response of G of S. Okay, let's do it. 0 times 2 is equal to 0. Okay, let's change the color again. Okay, so let's do the same thing for the high frequencies. Minus 90 times 2 is equal to minus 180, so it will be here. Okay, let's concentrate on the mid frequency point. Minus 45 times 2 is minus 90. It will be here. As you can see, if you follow the same structure, we will obtain a very similar picture, but it has a bigger size in the interval. Okay, so the first order system starts from 0 degrees, goes to minus 90 degrees, and this critical damp system starts from 0 and goes to minus 180 degrees, but it's effectively cornering, like changing direction at the same frequencies. Okay, from this perspective, as you can see, it's very easy to understand the Bode plot of a critical damp system from the Bode plot of its subsystem, which is the first order case. Okay, so let's look at the actual and approximation differences. As you can see, when I concentrate on the critical damp case, you can easily see that the errors are getting bigger. Indeed, errors are 2 times bigger in the critical damp case, okay, which is an expected result because since we are multiplying the Bode plots by 2, we are also multiplying the errors by 2 at each frequency. Okay, so for example, in the first order case, the highest error occurs at the corner frequency, which is 3 dB. 3 dB. And for the critical damp case, it's equal to 6 dB. Okay, this is as simple as that. Now, since we are okay with critical damp case, let's move on to overdamp case. Okay, overdamp means that psi is larger than 1, and it means that I have 2 real roots on the negative real axis, or if it's not a minimum phase system, it can be also in the right part of the real axis. But let's concentrate on this. Okay, what are we going to do? In the Nyquist plot, we generally plug j omega instead of s. We do the algebra, try to figure out the polar plot or Nyquist plot. But in here, we are using logarithm. And multiplication in the logarithm is super easy because we simply add things in the logarithmic scale. Okay, so what I do is I divide it into 2 parts. Okay, s plus 10. As you can see, both the plots are given for both cases. Okay, since a magnitude plot is using the logarithmic scale, both a magnitude of g is simply equal to, for each omega. So let's clean everything and to make it easier. Okay, so m of g for each omega will be equal to m of 1 over s plus 1 omega plus m of 10 over s plus 1 omega. Okay, it's coming from directly the features of the logarithm. So what I need to do is, at each range, I need to add the magnitude response of this and this. Let's do it. Okay, 0 times 0 is equal to 0, which is good. Okay, this is easy. So in this region, as you can see, 1 over s plus 1 is still 0 dB. So technically it will follow the 10 over s plus 10 case. Okay. So in this region now, as you can see, we have responses in both cases. So let's look at this. This is 1, this is 2, so it should be 3, it should be here at this point. So this is 2, okay, this is 3, so it will be equal to 5, it will be here. Okay, so if I follow the lines, I obtain this. Okay, good. So let's look at this. This is constant, so it has a 0 dB per decade trends. In this region, since this interval is equal to 20 dB, in this region, which is like mid frequency, the tendency is equal to minus 20 dB per decade. Okay, but in the high frequency region, when we pass the cutoff frequency of both low pass filters, as you can see, it has a tendency of minus 40 dB per decade. And as I told you before, for all second order systems at the higher frequencies, you need to see a line which has a minus 40 dB per decade tendency. Okay, so this is true. And let's look at the phase, and we will see that we have the same structure. Okay, so okay, this is good. Everything is nice. Okay, so what is phase? Okay, phase of g at omega is equal to simply phase of 1 over j omega plus 1 times 1 over, not 10 over j omega plus 10. Okay, so it's multiplications. So what we do with the phases, we just simply add them, j omega plus 1 plus phase of 10 divided by j omega plus 10. But this is the phase of the first system. Okay, and the second one is the phase. Okay, so let's clean this. Phase of the second system. Okay, so I do the same thing for the phase. I just look at the responses of both systems. This is belongs to 1 over s plus 1, and the second one belongs to 10 over s plus 10. I just add the phase response of each transfer function to obtain the total phase response of g. Okay, so let's look at this part. It's 0 times 0 is equal to 0, which is good. So in this region, this is still 0, so I need to follow the second transfer function. In this region, I see a response in both cases. If I just add them, I will simply obtain this. Okay, right? So I should obtain this if I'm not, no, I'm wrong. So let's clean that. In case I do mistake, let's concentrate on this point. So this is 1, this is 2, so it should be 3, so it will be here. So it is coming to this point, right? Okay, so, and then this is constant, this is not constant. So at this point, it is 2 times 2, it is 4. It's going like this, and then we finish the phase response. Okay, so what happens? It starts with 0, then it technically goes to minus 45 degrees in 1 decade. Then it goes to minus 135 degrees in a decade. After that, again, there is a change of trend. It goes to minus 180 degrees in 1 decade. And after 100 radian per second, the phase becomes constant and it's equal to minus 180 degrees. Okay, so it starts from 0, it goes to minus 180 degrees. For all second order systems, phase starts from 0 and goes to minus 180 degrees. But of course, if the system is stable, minimum phase system. Okay, yeah. So now we are done with the overdone case, and as you can see, it's not that hard. We simply decompose into subparts which are first order and which we already covered the details and features of the first order systems. Okay, so let's look at the results. I think one of the most interesting, in my opinion, things is, as you can see, the both phase and magnitude seems to be more correct in terms of approximations for the combined system G, not the first order case. It may not be true, but the basic idea is, in the critical dump case, we are multiplying the errors because errors are occurring at the same frequencies, but since these has different corner frequencies, their error are kind of distributed, and the, combined case somehow seems to be okay, both for the phase and the magnitude. So the take-home message is the approximations are pretty good for overdamped systems. These asymptotic approximations, they were already good for first order systems. For critical damped systems, it was okay. Now we will see what happens when we have an underdamped response, when psi is less than 1. Okay, so here, in order to show the big picture or the problem, I plotted the underdamped Bode plots of this system. Okay, so as you can see, omega n is equal to 1 radian per second for both cases. And as you can see, the cutoff frequency for all cases happening around this frequency. So it's not exact cutoff frequency, but the corner frequency, let's say. Okay, this is 1 radian per second. Okay, so if I change omega n, I would technically shift everything in horizontal scale. Okay, good. So let's look at the results. Okay, so psi is equal to 1, which is critical dump case. This is 1. Then I decrease the psi 1 over 2, 1 over 4, 1 over 8, 1 over 16 in a geometric scale. As you can see, let's look at the phase first. In this direction, psi is decreasing. What's happening is, and this is my approximation, if I use a critical damp approximation, my errors are increasing. Okay, but in this case, psi is increasing in this direction, and this dashed line is my critical damp approximation. It's kind of weird because the biggest error, of course, occurring when psi is equal to 1 over 16, and it will be even worse for smaller psi's. But the best approximate response is not occurring when psi is equal to 1. Instead, for this case, psi is equal to 1 over 2. Okay, so this is kind of interesting because indeed, if we do the maths, basically take the derivative with respect to psi and try to find the best possible approximate response, we will see that when psi is equal to 1 over square root of 2, error between actual Bode plot and approximate Bode plot will be minimal. Okay, but for the phase case, the best approximation seems to be still the critical damp case. Okay, so what is the take-home message here? In general, it's really hard to approximately capture the behavior of underdone systems by hand. Okay, so what we do is in this class, for if your system is second order and underdone, it's okay to show it only using the critical damp approximation.